Alright, exponential growth and logarithmic models. Let's jump right into it. Such a fascinating subject, why would we wait? Alright, so we have the four most common models, and the four that we're going to use in this section are exponential growth and decay. Alright, that's what this video is going to focus on, but there's also something called a logistic growth and a logarithmic model, and we will tackle those in class. So let's jump right into some word problems. So in a research experiment, a population of fruit flies is growing according to the law of exponential growth. If after 2 days there was approximately 100 flies, and after 4 days there were 300 flies, how many flies will there be a week into the experiment? Alright, so one way we could do this, if we had a calculator, we could plot these 2 points on a scatter plot, and then just like we did linear regression, we could find an exponential model to fit through those 2 points. Alright, but since there's only 2 points, and we can do this by hand, we don't need a calculator, at least for the, we might need a calculator to approximate some decimals, but in class we're going to find some data and do a line of best fit. But because here there's only two, or an exponential curve of best fit, but here since there's only 2 points, we could just straight up come up with a exponential model that goes through these 2 points. So it says first that it follows the law of exponential growth. So that means we're going to use this model right here. So y, where y is the population of flies, equals a times e to the bx power. And then it says after 2 days there was approximately 100 flies. So we have one data point, 2 comma 100. And then after 4 days there was 300 flies. So we have the point 4 comma 300. So what we're going to do first is plug those 2 points into 2 separate models, and then we're going to solve for a and b. So when we plug the first point in, we get 100 is equal to a times e to the 2b power. And we plug in 300 for y, then we're going to plug in 4 for x. So now we have 2 separate equations and 2 variables that we need to solve for. So we're going to use substitution. So one thing that we could do is multiply everything in this top equation by 3, so that we get 300 on the left side, and then on the right side it'd be 3a e to the 2b power. Now since both of these equations equal 300, alright, so notice 300 is equal to that and 300 is equal to that, we could set these equal. So that's what we're going to do. We're going to set a times e to the 4b equal to 3a times e to the 2b power. So we're going to divide both sides by a, that'll cancel that out, and also divide both sides by e to the 2b power. And on the right side we just have 3, and on the left side we're going to have e to the 2b power, because we're dividing two numbers that have exponents and the bases are the same, so we could subtract the exponents. So 4b minus 2b is 2b. Now if we put this in log form, base is e, so it's a natural log, answer is 3, equals the exponent 2b. So to figure out what b is, we divide both sides by 2, and we get b is equal to the natural log of 3 over 2. So you type that in your calculator, you do the natural log of 3, make sure you close the parentheses first, and then divide by 2, and you should get 0.5493. Alright, so at this point, our model is y is equal to a times e to the 0.5493x power. Alright, so now we just have to figure out what a is. So now we just plug in another data point and then solve for a. So if we were to plug in, we could actually do this without a calculator. If we were to plug in 100 for y, then it would be a times e, and then instead of using the decimal approximation, I'm going to use the natural log of 3 over 2. Alright, and then since we plug in 100 for y, and we're using this point, we got to plug in 2 for x. Well, watch what happens. These 2's cancel. E to the natural log of 3 is just 3, so it's 3a is equal to 100. Divide by 3, and you get 100 over 3. So approximately 33.3 repeated. So now to figure out how many flies will there be a week into the experiment, we have y, that's what we're looking for, is equal to a, which we now know is 33.3, or we can leave exact as 100 over 3, times e to the b power, and we found b to be about 0.5493, but with a calculator we could just type it in exactly as the natural log of 3 over 2. I'm just going to use the decimal here. Alright, and after a week that'd be 7 days, so we plug in 7. Alright, and if it said just give me the model, then I wouldn't plug in 7, I'd leave 7 as x. But since we want to figure out how many flies a week into the experiment, we just type that in our calculator, and we get about 1,508.7, alright, approximately. So that population is growing quite fast. And I hope that you follow along with the calculator. Probably should have told you at the beginning, but if you want to go back and crunch these numbers and make sure you know how to use the calculator, I mean, it's not one of the harder calculator things we do. We'll do the harder stuff in class, but just make sure you know how to approximate those decimals, and that just involves typing into a calculator. Alright, let's try another one. So another common example of exponential decay is radioactive decay. So radioactive materials and some other substances decompose according to a formula for exponential decay. So the amount of radioactive material present, or A, at a time t is given by the formula y is equal to A times e to the negative kt power, so as long as k is positive. So the negative is already factored in to the equation, so like the rate is negative if something's decaying, like it's losing material over time. So if you get a positive answer for k, then in your model it should be negative k. Like, just don't plug in a double negative and then turn it into exponential growth. Just be careful of that. The negative part is already taken care of in the formula. So a radioactive substance is often described in terms of its half-life. So that's the time it takes for it to decompose to half of the original amount for when you started counting. So here's an example. After 500 years, a sample of radium-226 has decayed to 80.4% of its original mass. Find the half-life of the radium-22.6. Alright, so we're going to plug stuff in. So we know it's exponential decay. So we have y is equal to a times e to the negative bx power. So we don't know the original amount, and we don't know b. But we know that when x was 500, it's going to be 80.4% of the original. So a in the model represents like the initial amount, because if you plugged in 0 for time, this part would cancel out, it would just become 1, and you'd get a for y. So that number in front of e in exponential growth or decay is always the initial amount. So we can express y in terms of the initial amount, because we know it was 84% of a. So 0.084a represents the original amount, 80% of that. Alright, so then we'll do e to the negative b, and then x we know is 500 because we set y equal to 80.4% of the original amount. So now we can divide both sides by a and cancel that out, and then put this into log form and get the natural log of 0.804 is equal to negative b times 500, and then we could divide by negative 500, alright, and that would cancel everything out, and we get b is equal to the natural log of 0.804. Do that first, and then divide by negative 500. And if you type that into a calculator, you get a small decimal. It's decaying, but it takes 500 years to only lose 20%. So it makes sense that the rate is low. 0.000436 as a decimal approximation. Alright, the exact answer is right here, the natural log of 0.84 over negative 500. So, Now, when we plug this into our formula, and actually this should be positive here. I apologize, I didn't mean to write that negative, because like I said, it's already taken care of in the formula. If now if we can look at our model, and we got y is equal to a times e to the negative 0.00436 x power. So what I was trying to say before is, like, in your final answer, the decay model should have a negative exponent. So to find the half-life, now we're going to see how long it takes to get to half the original value. So for y, we're going to plug in 0.5a, and then the original amount is just a, and then times e to the negative 0.00436 power, and then we got to solve for x. So the thing is, we don't even know what a was, the original amount. We don't need to find it to do this. So we're going to divide both sides by a, and then we could take the natural log of both sides, and we get the natural log of 0.5 equals negative 0.00436x. Alright, and then we're going to divide by that negative 0.00436. Alright, and then we get x is equal to about 1589.8. So that is the half-life of that isotope, radium-226. That's how long it takes to decompose to half of the original amount. So if your great-great-great-great-great-great-grandfather from 1600 years ago left you in his will 10 grams of radium-226, then 1600 years later, you would only have 5 grams. But you know what? It's better than no radium. That's what I always say. Alright, let's see. I think this is the last slide. Yep, you're off the hook. So thanks for watching, and have a nice night or day whenever you're watching it.